I'm beside myself. We're talking about the weak law of large numbers. Let's continue to do that. I guess there's a challenge with the posting of the homework. I hope it'll be up today. Weak law of large numbers, as we described it last week, was given by the expression that we have here. And I need a pointer. Let me see if I have a pointer. No, that isn't going to work. How about my room key? That doesn't work very well, does it? Yeah, I guess that's okay. Yeah. Oh, thank you. Is this mine? No. Because I have one just like this. I have one. Oh, you got it from the office cabinet. Okay. So it belongs to the government. Thank you very much. Thank you very much. Okay, here's what we determined last time. The law of large numbers basically says that the average approaches the mean, and it approaches the mean in this way. There's various statements about the law of large numbers. This is the weak law of large numbers. And so the nice thing is that the probability as n goes to infinity that the average minus the mean is less than 10 to the minus billion is equal to 1 for all values of epsilon. So therefore it's a very, very powerful statement. It's one that we use. Then we also talked about last time the so-called strong law of large numbers. And I won't go through that. But let's look at an application of the weak law of large numbers. It can actually be used to give what I refer to as sloppy confidence intervals. They're sloppy in the sense that the resulting confidence intervals are very, very liberal. And that if one were to look at a problem a little bit more precisely, one could get more conservative confidence intervals. Let's take a look at repeated Bernoulli trials. We know that a couple of things about Bernoulli trials is the expected value of the Bernoulli trial, an individual Bernoulli trial, is equal to P. We also know that the variance of the trial is equal to P times 1 minus P. Now, here's the problem that we're going to do. We're going to look at estimating the probability P of a Bernoulli trial. We know it's a success or it's a failure. We assume that the trials are IID, but we would like to compute the probability of success. And we would like to be able to state something about the probabilities of success in terms of its confidence. Since we don't know P, we don't know the variance of P. But we do know that for repeated Bernoulli trials, the variance of a single Bernoulli trial is P times 1 minus P. Well, if we were to look at this as a function of P, we know that the variance would have to be less than or equal to a fourth. The biggest value that this variance obtains is when P is equal to a half. So therefore, no matter what the value of P, it must be less than or equal to its maximum value, which is P is equal to a quarter. Now, with this, let's then look at the weak law of large numbers as we saw it before. This is the general statement, the probability that the average, so we repeat this Bernoulli trial. For example, we're throwing darts at those circles on the dartboard, and we're seeing whether we get a success by getting the dart within the circle or a failure because the dart doesn't go in the circle. And we repeat this for n times. We do this n times. And we come up with a result, but how accurate is it? We have a feeling that the more darts we throw, that the more accurate our result is going to be. Indeed, that's what the weak law of large numbers tells us. So the probability that the average we get, I don't think it's showing on the screen here, but there's a magnitude sign here on both sides. The probability that the average minus the expected value of an individual Bernoulli trial, which is P is less than or epsilon. Here is the general statement that we had previously. So the statement in this part is the weak law of large numbers with P being substituted for the expected value of X. And this is the expression we have. Well, we have an expression here for the variance of X here, so we can actually make this continue the inequality and put, instead of the variance of X here, put the 1/4 in the denominator. Does that make sense? So therefore, we're assured then that this probability exceeds or is equal to this number.
How did we pick the 1/4?
We picked the 1/4 because we know with a repeated Bernoulli trial that the variance of a single Bernoulli trial is p times 1 minus p, and the biggest that that can get is 1/4. So therefore, there's not an equality here. It must be greater than or equal to this, and it's equal to this only when p is equal to 1/4. Otherwise, this is a strict inequality. So this is a repeat of the expression we had at the bottom of the previous screen. And here's a question we have. Suppose we want to be 95% or more sure that the result is within 1% of being correct. Now let's think about that, for example. 1% of being correct. So we want to determine the probability of success in the Bernoulli trial within an accuracy of 1%. And we want to be 95% sure that our estimate of the probability P is within P plus or minus 1%. That's what a confidence interval does. Well, this statement of what we want allows us to put numbers into this expression. We would set epsilon equal to 0.01. Why is that? Because we want to be sure within a 1% confidence that the probability that A minus P is less than or equal to 0.01. And since P goes between 0 and 1, we'll assume that epsilon is equal to 0.1. Now, if this indeed is the case, then this other expression, we want this probability to be greater than 0.95 because of 95%. So therefore, this expression we set equal to 0.95. Well, we have epsilon squared, because that's the degree of confidence that we'd like. The only thing that remains is to solve for n, which will tell us how many trials we have to repeat in order to gain the probability to this confidence. If we solve for n, we find out that n is equal to about 50,000. So we have to actually do 50,000 Bernoulli trials in order to make sure that the probability that we get is within 0.01. This is actually probably a misstatement. It's within 0.01 of being correct. We need 50,000 trials to make sure that that's true, that we have plus or minus 0.01, and we're 95% sure that this is indeed true. This, of course, is using this Chebyshev inequality, and again, this is a loose bound. So this is probably an overstatement because the bound is loose. We could probably use other analysis and actually get the bound to be tighter, in other words, n to be smaller, but the Chebyshev inequality, which gives us kind of sloppy bounds, gives us 50,000. And I will say that there are better ways to do this. In fact, we'll see better ways before the course is over. So any questions on doing that? On this? Kind of an interesting result. We know that the mean is represented as the average. And the law of large numbers says the average approaches the mean. What about the variance? Well, the variance also has a variance, which many times is referred to as a sample variance, which we estimate from the data. We usually have this on our programmable or our calculators, where we can actually enter in data and hit one key and we'll get an estimate of the variance out. Well, this isn't the actual variance. It's an estimate of the variance, because the variance that you get out of the calculator when you enter in all of these values is a random variable, right? It's a random variable. We hope that it is close to the variance, but indeed it doesn't need to be. So we can approximate the variance of x as approximately equal to v, which is given by this expression, which is what is used for sample variances in MATLAB and in programmable calculators. Now, what is interesting here is that for a minute, ignore the 1 over n minus 1. Ignore the minus 1 portion of that. If we ignored the n minus 1 portion of that, you'll notice that this expression is simply the average of the square of the difference, right? So if we had a 1 over n instead of a 1 over n minus 1, this would be an average. It would be an average. It wouldn't be an average of x bar, but rather it's an average of this quantity, right? So it is an average. The fact that it's an average means we can apply the law of large numbers to it again and say, hey, since this is an average, we're assured that in the limit, an average will approach the mean. The mean of this particular average turns out to be the variance. And indeed, we can apply the law of large numbers here also. Here's something which is very interesting. If the x's are IID random variables, then it turns out the average and the variance are independent of each other. Isn't that interesting? That the random variables of the average and the variance are independent of each other. We won't show that, but that's a very interesting result. Looks like a constellation, doesn't it? Oh, that's my face. Okay, never mind. It was, there's something funny with the screen. Somebody sneezed on it or something. Okay, I thought we'd have a little bit of fun talking about how to gamble, because I'm sure that's near and dear to all of our hearts. Hopefully you're convinced that for lottery gambling, your chances of winning are about the same whether or not you buy a ticket, right? But here's a case where if you own the casino, you'll never win at gambling unless you're the owner of the casino and can set the odds. If you're a player, law of large numbers. The law of large numbers says you will always lose. And in fact, all the gambling casinos operate on the law of large numbers. You might go in and you might win here and there, but you're going to lose eventually if the odds are properly set. We're going to take a look at a gambling sequence which actually imposes the law of large numbers in kind of a neat way. Here's the idea for the optimal betting. You're going to play a sequence of Bernoulli games with a chance of winning p greater than a half. If you do not play in a gambling scenario in a repeated Bernoulli trials with a probability exceeding 1/2, you're going to lose. There's just no doubt about it. Yes?
What if you're getting better than 2-to-1 odds, though?
Good point. I'm talking about even odds here. Okay, this is with even odds. If you have 2-to-1 odds, you can always take that 2-to-1 odds, fold it into the probability, and come up with a new probability of winning with even odds. Okay? So you must have a probability greater than 1/2. Why must this be? It must be because the law of large numbers says that if it's less than 1/2, you're going to lose everything you have eventually. It might take a long time, but they'll get it eventually. But here's a different scenario. Suppose you are the casino, or you're playing a game with somebody that's kind of dumb in probability, and you're playing a Bernoulli trial and your probability of winning is greater than 1/2. You start with a stash of money, which we'll call D dollars. So you start with, say, $10. You don't have an infinite amount of money. You're going to bet and lose. If you bet and lose, you lose what you bet. For example, if you bet the entire $10 and on the first game you lose that $10, you're done. Okay? If you bet $5 and you lose, well, you lose the $5, but then you have 5 more to play with. On the other hand, if you win, your bet is matched. So if you play $10 and you win, then you are going to get $10, so you have $20 in your stash. Okay, you get the idea? Very simple Bernoulli trial game. So this is the scenario that we have. Now, the question is, your probability of winning is 1/2. What can you do to leverage this probability of winning being greater or equal to 1/2 in order to take all of the other person's money, right? Clearly, you don't want to bet everything. There's the idea, I think, in gambling, at least I've heard on the movies, where if you win, they said, let it ride, which means that you play it again, right? You take all of your winnings and you let it, you continue the bet. Well, if you let it ride long enough, even if your probability of winning is 0.9, if you keep letting it ride, what's going to happen in the end? You're going to lose it, right? Because eventually it's going to come to that point where you lose everything. So clearly we don't want to bet everything all the time. On the other hand, we want to bet something. What happens if you play that Bernoulli trial and never bet anything? Well, you just sit there with your $10, right? So clearly the optimal bet that you want to do is somewhere between the $0 and your entire stash. And that's the question that we're going to address and answer. We're going to say, and we're going to address it the following. What percentage of the money you have should you bet given the probability of winning? Now, the percentage is something you can always do. If you have $1 or $1,000 or $1 million, and we'll assume that pennies can be divided. Okay, we're going on a continuous model here. But no matter how much money you have, you can always bet a percent of what you have, right? And if you only bet, for example, 50% of what you always have, if you always just bet 50%, then, gosh, you'll be playing forever, right? Of course, your bets will become diminishingly small. So that's the question that we're going to ask ourselves. What's the optimal percent bet for steady state winning? Okay, here's an example sequence. Let's take an example sequence to try to get a feeling for the math. Here's what we're going to do. Suppose we play the game and we win the first time. Don't forget D is our stash. So if we win the first time, we have our stash D plus the percentage of D that we bet, right? This is the amount we had originally. This is the amount we bet. We won, so that is added to what we originally had, right? So this becomes our new stash at the end if we win the first game. And we don't know what this percentage is. That's what we're trying to figure out. Should it be 50%, 25%, 75%, etc.? Follow? Do you? Okay. So let's suppose on the second game we lose. Well, we would have bet a larger percent. We would have taken D1, and whatever that percent was, we would have bet D1. If we lost, then our new result would be D1 minus what we bet, which is the percent of D1 that we had. This percent, by the way, that I have it here is a variable. I thought that a nice percent sign, nobody ever uses percent as a variable. So percent is a variable here. So if we look at the math, it's what we had minus what we bet, the percent of D1 that we bet. And then if we put all of this together using the distributive law of algebra. Do you know algebra was named after an Arab? Do you know that? The name algebra? Because algebra was invented by the Arabs. Anyway, D2 is equal to this relationship if this is under the scenario that we win and then we lose. Now we're going to lose again, and if we lose again, we get D2 minus the percent of D2 that we lost, and if we put the algebra to it, we get this expression. Suppose now we win, and I think you can see a pattern taking up here, that right now we have 2 wins and 2 losses, right? Well, it turns out that for every win, we take 1 plus the percentage, and we raise it to the number of wins, and we take 1 minus the percentage, and we raise it to the number of losses. So by induction, we actually have the following scenario. If we do n trials, and we have k wins in those 10 trials, meaning n minus k losses, then our total amount that we have at the end of this time is 1 plus the percentage raised to the kth power, time, that where k is the number of wins. And notice 1 plus, this is going to be a number bigger than 1, so it's going to increase the stash. It's going to be 1 minus the percent that we bet, raised to the n minus k power, where that's the number of our losses. And this then will be, for a given sequence, this is going to be our stash at the end of n games. Okay? Now, what would we like to do? We would like to find out the value of percent that maximizes the expected value of D. Okay, here's the expression that was at the bottom of the previous screen. What value of percent maximizes D under the assumption that n is large? Notice for small numbers, you have luck, right? But for large numbers, luck and probability don't enter into it. It's fixed. Now, maximizing D for a fixed value of n is the same as maximizing the log of D. Now, let's talk about this. D sub n is a function, and log is a strictly increasing function. So maximizing the function is the same as maximizing the log of the function. They're the same thing, since the log is a strictly increasing function, right? And I'm going to, just for reasons here, divide it by 1 over n because it makes the math easy. So let me call b sub n is equal to 1 over n log of d of n. And if I find the value of the percent that maximizes b, because the log is strictly increasing, that's the same as maximizing d, under the assumption for a fixed n. So if I look at b of n, which is this new thing I want to maximize, I get the expression shown at the bottom of the screen here with some logarithms. Should there be a 1 over n in the last term? Yes, there should be. Should there be a 1 over n in the last term? Yes, there should be a 1 over n here. Thank you. Yeah, there should be a 1 over n accompanying the log. What's going to be interesting, though, is what are we going to do? We're going to differentiate it and set it to 0. Old calculus 1 sort of stuff. And this log of d is going to go to 0. So if we, before we do that, though, here's what we're going to do. And this was clever. This was done by a guy at Bell Labs, I believe in the 60s. I have to find the name, but I do know it was a Bell Lab person. Here's something which is interesting. We can apply the law of large numbers. Now, we're applying it in a sloppy way because we're not applying it in the way the mathematicians would do, which is the limit of the probability is less than epsilon is greater than or equal to. We're going to actually say that in the limit, the number of wins divided by the number of trials is going to be the probability. This is the law of large numbers kind of written very tersely for repeated Bernoulli trials, right? The number of k over n is equal to p. Similarly, n minus k over p, this is the number of losses divided by the number of trials, is equal to 1 minus p. So applying this, then b sub n, it had a k over n here and a n minus k over n over here. It's the reason we divided by n, and there should be, again, a 1 over n here. But under the assumption that we apply the law of large numbers, and this equality takes hold, that we do indeed have a probability of p, which occurs here. Now, this is very nice because it's taken n and k out of the equation. Notice we no longer have k and n. We've gotten rid of them by implying the law of large numbers.
Did you say there was a special reason we let the limit of k go to infinity rather than n go to infinity?
No, I didn't. That's a typo also. Thank you. This should be n going to infinity. N going to infinity. Thank you. But k goes to infinity too, but it's a lot more awkward to think about. I think that rigorously the statement is correct, but I'd rather put an n there. Okay, let's take a look at this then. Again, this should be an n and this should be an n. So we have this relationship here, and we want to just take the first derivative and set it to 0. So we take the derivative b with respect to the percent, and we set that equal to 0, and doing so gives this relationship. And what do we want to do? We want to solve for what the optimal percentage is, and then make sure it's a maximum. We certainly don't want to minimize it. The percent is very interesting. It's simply twice the probability minus 1. That is the optimal percent that you should bet. Notice that the percent that you should bet, kind of some interesting sanity checks, is that if p is less than a half, what percent should you bet? A negative percent, right? Which means how the other guy bet. Is one way to think about it. So this percent of betting only makes sense if p is greater than a half, right? Which is something that indeed you would expect. So that's a little sanity check. So if we substitute this into the original equation for the amount of money that you're going to have at the end of n trials, it turns out to be this relationship here, that the amount of money you have at the end of n games in the law of large numbers. Now, this is asymptotically. You might win and lose and lose and win and win and lose. But eventually, asymptotically, you'll come to this expression. You're not supposed to talk while I'm talking. Okay, if you have a question, go ahead and raise your hand. Yeah.
Can you go back a couple slides and explain where B came from?
Oh, okay. Where did D come from? We get to gambling. Everybody becomes interested. Okay. What I'm simply doing is it's easier to find the maximum of B than it is for D. And what I'm saying, for a fixed value of n, maximizing B is the same as maximizing D, since the logarithm is a strictly increasing function. Okay.
Do like the door problem, the hall problem with the doors. Is there, would it be better if we went back and did this and said if you lose, maybe change your percentage, if you win, change your...
Oh, you could. We are solving a very specific problem. Now, is this the most you can win? I don't know. I can't guarantee this. It very well could be. We are solving the problem if you want to be a machine and just bet a percentage of your stash every time, whatever that is, and you want to find the percentage of that you bet in order to maximize your winnings, this is what we do. A separate question is there a better way to make more money in the limit? And I don't know. I don't know if this is best or not.
But in this case, changing your bet based on what just happened, I mean, assuming they're independent, wouldn't make any sense, right?
Because it depends, and the question is making your bet currently based on what just happened. Maybe that isn't wise, because what just happened is going to be statistically independent from what happens. The only case where you might want to take into account what you previously did is the degree of your stash. Okay, maybe if you were down to 5 pennies, you'd want to bet more liberally or more conservatively. I don't know. So you're right, in terms of the strict probabilities, they are still independent, but there might be another scenario that you play around with.
I would go back to the problem on the test, the first problem on the test. If we know we just lost 10 times in a row, and the average has to say it's a half, it's a little greater than a half, the probability is a little greater than half, then, you know, it would seem we've got to come out on the mean.
But you might want to go back and do some adjustment. Okay. If you can work out something to that, I'd like to see it. We'll go to Vegas. Okay. No, you cannot win in Vegas, though, unless you own a casino. So we'll have to go to Vegas and get a gambling license. That's what. Okay. So this is what D becomes. Which is very interesting. Now, another thing, this is what D becomes, but D also has the K and the N over K in it. So I'm going to raise D to the 1 over N power. So I'm going to make K over N equal to P, and N minus K over N to 1 minus P. So therefore, invoking a law of large numbers again, I obtain that the nth root of D is equal to this expression, which is kind of nice since I have kind of sucked out the K value in there, and we only have the value of N. By the way, another thing. I mentioned that P must be greater than a half. Here's another sanity check. Say you had a 100% chance of winning. What would you bet every time? Everything, right? And notice, if P is equal to 1, what percent should you bet? Everything, right? If you had no chance of winning, or no, well, P is equal to a half, which is a 50-50 chance of winning. This formula says you shouldn't bet anything. Go home. You're wasting your time, because your expected value at the end of 4 all-nighters is going to be what you started with. Your expected value. So this is the expression that we had, and this is the actual relationship, and the ratio of your winnings on the nth term divided by D is given by this expression. And we can actually give this a little bit of personality by talking about your number of turns to double. It's kind of the opposite of a half-life. It's the double life. How many turns do you have to take in order to double your stash? You get the idea? So the number of turns to double your stash is obtained by setting this to 2. So if we set this to 2 and we solve for n, we will get the number of terms it takes to double your money. This is a geometric curve, right? So the concept of half-life or doubling time is totally appropriate. And if we do that, we get the n double. This is the number of times to double is equal to the expression here. I look at that and I say, I don't know what that means, but we can plot it. And this is kind of what it looks like. This is the probability from going from 0.6 to 1. I know you can't see that on your screen. You might have been able to print it out, but this goes from 0.6 to 1, and this goes from 0 to 3.5 full scale on a linear scale. And we couldn't go to 0.5 because at 0.5, what's the number of trials it takes to double your money? An infinite number, because it never happens, right? So we had to start at something which made it manageable. So we started at 0.6 because this curve asymptotically goes up and hits infinity at p is equal to 5. So for 0.6, this is kind of interesting, it takes about 3.5 turns to double your money. At 0.85, if your probability of winning is 0.85, then it only takes about, 2 or 3 turns to double your money on the average. And again, this imposes the law of large numbers, and you need to keep that into account in interpreting this. So I thought that would be a fun thing to talk about. It's the law of large numbers, but a little bit more sophisticated than the dart throwing and just computing the average and saying that that's equal to the mean. Yes?
Isn't that 35? Because otherwise it's 3.5.
Oh, you're right. In fact, that doesn't make sense, does it? This is 35. Yeah, this is 35. Did I say 3 point? I did say 3.5. That's 35, from 0 to 35. So if you're at 0.6, it takes 35 turns, not 3.5. Thank you. Big difference, huh? Big difference. The only difference is how much time you have to stay there, though, right? How many games you have to play. That's the interesting part. If you can win and you have all the time in the world, if your chances of winning are greater than a half, then you can win as much as you want if you can spend as much time as you want playing. Any questions on this? Yeah.
On the thing where you did the derivative, the dB percent,
Yes.
it seems like if p is 1/2, then it shouldn't matter what you bet, because eventually you're going to come out even, right?
Yes. If p is equal to 1/2, it doesn't matter what you get because you're going to come out even eventually.
But the only way to do the derivative really is to make percent 0. So that's, the two things, the information I'm getting from the derivative doesn't really jive with my intuition on what I should do if I really work at it. You see what I'm...
No. I have no idea what you just said.
My intuition, and I think what you just said, says that if p is 1/2,
Yeah.
it really doesn't matter what I bet. So the derivative of what I'm going to win with respect to how much I bet should be flat. It should be 0, regardless of what I bet.
Your derivative is 0. Oh, you're saying if the percent is equal to 1/2.
I'm saying if p is equal to 1/2.
Yeah, if p is equal to 1/2, you go back here, and this equation doesn't have a solution if p is equal to 1/2, does it?
It does. Percent is
No.
still 0.
No, if percent is equal to 1/2, 3/2. I don't know, and I prefer not to waste time on it. The only thing that this tells us is where this function maxes out, okay? And this is a function which goes through the origin or goes through the x-axis, if you will, as a function of percent. And giving any other interpretation to it, I don't know if that's meaningful or not. Okay, any other questions on that? Let's take some notes. At p is equal to 1/2, the number of times to double is equal to infinity, which is true. And at p is equal to 1, what's the number of times to double? If you have p is equal to 1 time, right? Every time you play, you double your money. And notice the p goes down here to a value of 1. So indeed, this does satisfy little sanity checks. What is this? Oh, this is P. I think I actually went to like 0.5, 0.0551. So this is 0.5, 0.55, 0.6, 0.657, all the way up to 1. So this scale goes down to 0.5 to kind of show you how you go up to infinity. We're in a log scale now. So this is 10, 100, 1,000, 10,000. So it looks like for about 0.56 that we have about 3,000 games that you have to play in order to double your money. Okay, if it's 0.51. Here's interesting. You know, you can go, and if you do run a roulette wheel, one of the things that you can do is put your money like on even or green. If you bet on a roulette wheel, even or green, your probability of winning is 0.5557. So that means you should bet, every time you bet, 11.13% of your money, but it takes you 111 times at the roulette wheel to double your money. Yeah, so write that down. Now here's a question, and I'll actually be giving to you this to you on homework next time. It's where there are odds associated with it. What if there are odds? Extend the problem to where you lose L% of your bet when you lose and get W% of your bet when you win. So if you bet $50 and you win, you don't get back all the $50. If you win, you get back $75, or you get back $25, depending on the odds. And if you lose, you don't lose it all. You lose a percent of it. You lose, let's see, W% of it. If you bet $50 and you lose, you don't lose it all. You lose half of it, or lose 1.5 of it, etc. It's a very easy matter to take the example that I gave you previously and extend it to the case where there are odds given to it. Okay, any questions on that? That was kind of fun, wasn't it? The answer is yes. That was kind of fun. Here's another little fun thing I want to do, and this is stochastic resonance. This, believe it or not, is a really hot topic. There are places in nature where the addition of noise enhances detection probabilities. There's an example of a crayfish, and the crayfish is very interested in certain type of fish swimming towards it. Unfortunately, the crayfish exists in a very, very noisy environment. And so how is he going to hear a fish coming up? Fish are pretty quiet too, right? If you have fish, they're really quiet. So what has he been able to do? This shrimp, I said crayfish, I meant shrimp. They kind of look the same though. This shrimp has embedded in it an actual detection system which is honed to look at very weak sinusoids, detect very weak sinusoids, and very powerful ambient noise. And it does it through a phenomena referred to as stochastic resonance. In fact, if you were to take that shrimp out of a noisy environment, put it in a totally quiet environment, his detection thing wouldn't work. That he actually relies, he or she, relies upon the ambient noise to do the detection. It's a very interesting phenomenon. So stochastic resonance is defined as follows. Oh, by the way, why a sinusoid? Because a fish coming at you is going to generate a sinusoid, right? With the fins? Seriously. So that's the reason that the shrimp is able to detect sinusoids. That's the reason their detection is tuned towards detecting sinusoids. So we define stochastic resonance as follows. It doesn't have a precise definition, but the general definition is a phenomena. Stochastic resonance is loosely defined as a phenomenon, the detection process, wherein the addition of just the right amount of noise improves the performance. Too little noise degrades the performance. Too much noise degrades the performance. In the middle, it's just right. Now, there are many dynamic models of stochastic resonance. The shrimp, for example, has a case wherein there's actually a control system with a varying state model corresponding to an oscillation. It's very complicated to analyze, but it's been done very, very nice. Here is another type of stochastic resonance, totally different from the crayfish, and it's as follows. We have a picture. This is a picture, by the way, of Robert Miyamoto. He's a associate director at the Applied Physics Lab at the University of Washington. And I use his picture without his permission. So, here's Bob Miyamoto. Now, what we're going to do is following. We're going to take each one of these pixels and we're going to add noise to it, and then we're going to clip it. So our noise process is the adding of noise to each one of these pixels, performing a clipping operation, and then seeing from that clipped, totally black and white image, whether we can recognize Bob Miyamoto. Here's an example where there is no clipping done. This is a 1 byte image, and the clipping is done at a half a byte. So this is the clipping which is done at a half a byte. This is a little bit of noise, and believe it or not, it doesn't show on the screen very well, I think because of the resolution. I don't know, can you see that this looks better than this or this? Neither one of them looks better than this. Huh?
Do you mean clipping or threshold? I mean,
Clipping at a threshold, we do the following. And I'll use the word clipping and thresholding interchangeably. We choose, this is a 256 byte image, 256 bit, 1 byte image. So we go to half of that, which is what? 128? If it's below 128, we set it to white. If it's above 128, no, if it's below 128, we set it to black. Above 128, we set it to white. So this is a totally black and white image. This is either a 0, totally white, or totally black, going from pixel to pixel. So that's what we mean by the thresholding. So hopefully you can see that in the process of doing so that this is not enough noise, that this is too much noise, and that this is, it turns out to be just the right amount of noise, although you can't see that really well. I don't know. It's kind of hard to see, but you can kind of make out his eyeballs here, right? Do you agree with me? You kind of can? But you can't see his eyeballs here, and you can't see him here. So that's kind of interesting. Okay. Well, let's look at stochastic resonance. By the way, here is the graphics are terrible. Terrible. Okay. This looks a lot better on the slides and on the computers that you have, hopefully. But what we did is we took the previous examples and put a little blur on them. And these are the blurs, and believe it or not, on the original image, this one looks a lot better than these other two. We blurred them out in order to make them nicer results. So again, here's too little noise, there's too much noise, and just right. Just like Goldilocks and the Three Bears, right? You remember that? Now here's an example of dynamic stochastic resonance, and unfortunately we have a situation where I've seen a better result. But anyway, this is actually different noise realizations. The noise is still random, but a number of different realizations are taking place and being averaged out. So the noise is changing dynamically. And so the eyeball has the ability to perform an averaging operation. And so here there's no noise added, so that's not as good. Here there's a little bit too much noise added. Hopefully here is the optimal in the middle. Can you see that on the screen? Okay. And actually, if you look on the screen, the one on the right kind of like looks pretty good, as well as the one second from the right. They both look pretty good. But what we're trying to do is capture the one on the left. And it turns out the one second from the right is closer to the one on the left. I can show mathematically. Okay. So here's the original image. This is too little noise, too much noise, just right in the middle. Well, let's take a look at stochastic resonance from this point. There was actually a paper just a couple of years ago in Proceedings of the IEEE that said stochastic resonance of the type we have just observed is due to nonlinear perception aspects of the human visual cortex or something like that. And we looked at this at APL, and the result is so simple. It has nothing to do with the nonlinear visual cortex. It's a simply expected value and law of large numbers sort of problem. So let's talk about this, and we'll show that indeed that this example and what we're seeing is something that can be described very easily with the tools that we have in mind. Here what we have, we're going to talk about signals now instead of images, but bear with me. X of t is some sort of signal. This, for example, would be the picture of Bob Miyamoto. And C of t is the noise which is added to the signal. Is that okay? And then what we do is subtract off the threshold, t, and we subject it to a unit step in order to get a value of z, which is either a 1 or a 0. It's 1, the unit step says it's 1 if all of this stuff is greater than 0, and it's 0 if the argument is less than 0. So this is just a simple description of the noise and the clipping. That's terrible. Terrible. That's a clipping sort of phenomena that we see. Do you agree with that? We take the original signal, we add noise to it, then we subtract off a threshold, and then we apply the unit step to get the binary function. Okay? So that's the signal. There's the noise. That's the threshold. That's a unit step function, and that's the binary stochastic process that we look at. We would like to look at the expected value of the stochastic process. We're going to look at the expected value of this. And the expected value of this process is equal to the probability that z of t is greater than 0. Right? The expected value is equal to the quantity times the probability of the quantity. The only quantity which is non-zero is 1. So it's equal to 1 times the probability it's equal to 1. So it's equal to 1 times the probability it's equal to 1. Plus 0 times the probability is equal to 0. Well, that's 0, right? So we don't have to worry about that. So only the first term in that expectation is required. If we manipulate this inequality, we find out that this is the probability that CT is greater than the threshold minus the signal. Hey, doesn't that look a lot like a cumulative probability density function? Yeah, it really does, doesn't it? For a fixed value of t, it's a cumulative probability density function. There should be a less than or equal to. But what it boils down to is that it's equal to 1 minus the cumulative distribution function for the noise of t minus x of t, where, of course, this is the cumulative probability density function for the noise. So that's interesting. The expected value of this binary signal is given by the cumulative probability density function operated on by x of t. Well, here is actually what has happened. This is the expression that we just had. And if we could zoom down a little bit. What happens is that the signal then, in terms of its expected value, can just be like a signal bouncing off a nonlinearity. Here's our original function x of t, sideways. T is going this way. And here's our function x of t. Here's t minus x of t. So this is equal to this subjected to a bias, just like in a transistor, and inverted, because we have a minus x of t as opposed to the x of t. So here is the x of t, and here is the t of minus x of t. Well, what is the expected value of z of t equal to? It's equal to 1 minus this cumulative distribution function. So let's look at this. Here is the cumulative distribution function. Remember, that's a strictly increasing function, as we said? Strictly increasing function. So 1 minus it is going to be a strictly decreasing function. We also call this the, the reliability function of the random variable. So what this says is that the expected value of x of t is simply this t minus x of t right here, bounced off of this nonlinearity, just like we would bounce it off a nonlinear amplification curve. And so we have the expected value of z of t here. And you'll notice the expected value of z of t, if we are in a linear range, will be exactly the same as x of t, right? If this is a linear range. So indeed, that's what happens. What's really interesting is if we add uniform noise. If we add uniform noise, which is just random with a uniform probability density function over an interval from minus alpha 2 to alpha 2, then what is a cumulative distribution function for uniform noise? It's a straight line, right? In fact, if alpha is equal to 1 byte, it's kind of like a 45-degree line, isn't it? It's a 45-degree line. And in fact, if we use uniform noise, that nonlinearity becomes exactly a linearity, and we would expect the expected value to be exactly equal to the original signal, which is really interesting. And I won't go through here. Whoop. And this is indeed what happens with the original Miyamoto resonance, which I'll show you here. Here, the slope of the noise is 0. In other words, it's uniform noise, but it has a 0 width. So there's no noise. Here, there is noise, but the noise is too broad. That is, the extent of the noise is too broad. For this particular case, in the middle, the value of the noise is at a 45-degree line, and in this case, the expected value of this just right picture is exactly equal to this result. Now, what I'll show you, and I didn't put in here, I meant to before the lecture, but did not get around to it, is actually showing an average of this to illustrate a law of large numbers. If we did an average of, say, 1,000 of these, then according to the law of large numbers, the expected value of that should approach the original value, if indeed this is equal to the expected value of this. So next time I'll show you some time averages, and this begins to become indistinguishable from this in about 30 or 40 averages. Really, really amazing. Okay. Whereas over here we're going to have too little of contrast, and over here we clearly have too much contrast. And here it's just right. Okay, any questions on that? Okay, if not, let's go ahead and take our break and meet back here when the big hand's in the 7. Thank you. I have on my website, under my facts, FAQS portion, a list of the top 10 theorems in mathematics with engineering consequence. The top 10 mathematical theorems with engineering consequence. They have to be mathematical theorems. Therefore, we do not do things such as Ohm's law. That's not a mathematical. That's from physics. Okay, Newtonian, Maxwell equations. Those are all physics. What do you think in math some of the most important theorems with engineering consequences are? Maybe theorems which you use quite extensively. Fourier transform. Oh, Fourier transform. Fourier transform.
That can be expressed as some sinusoids.
Oh, the decomposition. I've never thought of that. The Fourier's theorem of frequency decomposition. That's not on my list, but maybe it should be. That's very good. That's very good. That's very good. Huh?
Where is this list posted?
It's on my facts page. Don't you have a facts page with your home page? Yeah, FAQS, frequently asked questions that people frequently ask you? No? Well, I was even thinking more basic than that. I think probably the most basic one is probably the Pythagorean theorem, right? Which we use and we take for granted. But could you prove it? Could you prove the Pythagorean theorem?
That's the
A squared plus B squared is equal to C squared. Yeah.
Can you prove what looks like
Well, with trigonometric identities, you can, but those are kind of, I think this is sort of derived actually.
Of course, I wouldn't have asked the question if I were not able to do it. Here's a very simple way to do it. Here are two rectangles inside each other, right? And we're going to compute the area of the rectangles two ways. It's a plus b squared, right? Right, a plus b squared. But that's the same thing as the little triangle plus 4 of the little triangles. Right? Plus 4 of the little triangles. If you simplify this, you get Pythagorean theorem. Pretty slick, huh? So, I don't know how rigorous a proof that is. Anyway, that's on my list. Euler's formula, decomposing a sinusoid into e to the j plus e to the minus j. Cauchy's integral theorem, integration on a complex plane, where you integrate around something and you just look at the poles inside. Very, very close to a Stokes theorem or a Gauss's theorem sort of thing, where you can either take a surface and you can look inside and see what's happening, or you can look at just what's happening on the surface and figure it out. There's a sequence of theorems which look like that. Any other ones? Or the one that I'm about to give you, and the one we're going to talk about right now, which is a central limit theorem, is also on my list. It is undoubtedly one of the most important theorems in mathematics with engineering consequences. Notice we have to put that caveat of being of engineering relevance in this statement, otherwise we would have to go back in the realms of mathematics. What was that theorem that they just proved like in the last 10 years? Yeah, Fermat's last theorem was just proved. No engineering relevance at all. No engineering relevance at all. But a lot of fun for the mathematicians. Central limit theorem. Central limit theorem is a very, very general theorem, and if you look in different books, you're going to get different statements of what the central limit theorem is concerned with. In general, the central limit theorem is concerned with the density function which originates from adding up a number of different random variables with known density functions. And what the central limit theorem says is that in most cases, most all cases, when you add up a bunch of random variables, and then you can take that sum and divide it or subtract off a constant or anything you would like. So a linear combination of any of these, of just about any random variables in the whole wide world, will come up to be a random variable which is Gaussian. And it actually has its roots in double E math. The central limit theorem is less of a statement in statistics as it is in the area of convolution. One way it says this is as follows. If we have a random variable x and a random variable y, and we have some sort of density function here and another density function here, and this is for the case of IID. The central limit theorem is not restricted to IID random variables, although we will prove it for IID random variables since the proof is the easiest. But for the case of IID random variables, if we have this density and this density, what's the result? It's equal to the convolution of the two. It's something that we've shown in two ways, very fundamental. So indeed, if we were to add up enough random variables, if we would add up 50 random variables, then we would take each one of the component probability density functions, and we would convolve it with all the other ones to come up with one big probability density function. The central limit basically says is that pretty independent of the shapes that are chosen to do this, if we were to have 50 of these different random variables, that eventually you're going to come up with something that looks like a Gaussian random variable, independent of the shapes. Now, this is an almost always case. There are exceptions. Let me point out to the exceptions. What do you think one exception is? Cauchy, yeah. The bad boy of the probability density functions. Deterministic. Okay. I might ask, for example, what is the random variable of, I think this is true, of professors in this room? What's that random variable? It's not a random variable, right? It's 1, right? I think. There might be some other profs here. But if I were to express that in terms of a density function, it would be a Dirac delta with unit mass at 1. That's deterministic. So if we have a deterministic number which doesn't have any probabilistic interpretations, the density function is always a delta function. What happens if you convolve a delta function with a delta function? What do you get? You get a delta function, right? So you can have a billion delta functions. You convolve them all together, you're going to have a delta function. But you can say a delta function is a special case of a Gaussian if you stretch yourself. If you pinch in the Gaussian, puff it up, it would be that. So there are exceptions. There are forms of the central limit theorem that say there are classes of random variables which you can add together. Because if you do add up 5,000 Cauchy random variables, you get a Cauchy random variable. So it does maintain its own identity. So there's different forms of it. The form that we're going to be interested in is as follows. Under very loose conditions, if we were to add up a number of random variables, we would obtain a random variable whose probability density function is a Gaussian. That is the central limit theorem. We went through the example in class, by the way, with the die. Do you remember that? And we looked at the marginals of the dies, and then we looked at the sum of the dies. The marginals of the dies were uniform probability density functions. And if we looked at the sum of the two dies, that is x plus y, we came out with a triangle, which was indeed the convolution of the two. And if we were to look at the sum of 3 dies, we would take that rectangular density function, convolve it with itself 3 times, and you would get something which already was looking pretty Gaussian. It would be still looking humpy very, very quickly. So that's an example. So with that as an introduction, let's look at the central limit theorem. We have already looked at the sum of random variables. We did this last lecture, and we looked at the sum of n random variables, which were IID, and we're going to define a new random variable. Sometimes this is referred to as the z form of the random variable. Anytime you subtract off the mean of the random variable, you subtract off the mean and divide by the standard deviation, that's called the z form. Because if your random variable has a mean and a variance, if you subtract off the mean and divide by the standard deviation, then z has a 0 mean and a standard deviation of 1. So that's the reason that we can subtract off the mean and divide by the standard deviation. It's done quite extensively. Now, specifically for the sum, we found out a few things. For the sum, what was the mean? The mean was n times the individual value of x under the assumption of IID, right? S bar, the expected value of x, was equal to n times x bar. This is something that we showed last time. We also showed that the standard deviation of s was equal to sigma, where sigma is a standard deviation of one of these random variables, times root n. We used this fact to show the law of large numbers. So therefore, for the specific case of the sum, the z value is equal to the expression which is shown in the right here. S minus n x bar divided by sigma root n, where sigma is equal to the standard deviation of one of these random variables. Okay? Here's what we'll show. This random variable has a mean of 0 and a standard deviation of 0. No, standard deviation of 1. In the limit, as n goes to infinity, this is a Gaussian random variable with 0 mean and unit standard deviation. That's what we show in the central limit theorem. Another way of saying that is the limit as n goes to infinity of the cumulative distribution function for the z is equal to 1/2 plus erf, where the error function is the integral of the Gaussian as we have down here. But this is exactly the cumulative distribution function for a 0 mean Gaussian with a standard deviation equal to 1. It's the CDF of a 0 mean unit variant Gaussian random variable. So this is the central limit theorem for IID random variables. Again, for the central limit theorem to hold, your random variables don't have to be IID. They can be of different distributions. They can even be not dependent. They can be very highly correlated, and the central limit theorem will still work. But it's easier to deal with this. It's easier to deal with this for IID random variables. There's the ERF table. Okay. Let me give you an example of, before we prove the central limit theorem, let me give you an example of the central limit theorem and its application. This was actually motivated by doing my taxes. I owed a lot this year. And I got in my taxes just about a month ago. For last year, penalties could kill you. But when you fill out your tax form, they allow you to do, the IRS allows you to do one of two things. They allow you to put in everything down to the penny, or to take each one of the figures and round it off to the nearest dollar, right? But you have to do it consistently throughout your entire return. So this begs the following question. Suppose that we do rounding off of cents in a column sum. So in other words, we have a column of dollar numbers, and I'm going to do two things. I'm going to add it up exactly to within the penny. Then I'm going to take each one of the components and I'm going to round it to the nearest dollar. So I'm going to take away the penny components and then add together those rounded figures. I'm going to get two different numbers, aren't I? Right? And the difference between the two numbers is I would say a random variable, because it's pretty clear that the cents value, if you're dealing with significant dollars, the cents value is going to be kind of chosen randomly. So X is the rounding error. And if we look at an individual rounding error, what is the rounding error equal to? Well, we can say that it is uniform from minus $0.50 to $0.50. That is, if I take a single number and I round it to the nearest dollar, then what is the density function of my exact result minus my original result? That's going to be my error, right? The error that I get by taking my exact result minus my rounded result, I maintain is going to be like between minus 50 cents and 50 cents. I know it's going to be discrete because we are quantizing to the penny, but if we were to treat it in a continuous fashion, this is what it would be. Do you agree with that? Right? That would be the error which is obtained in rounding. So X is the rounding error, uniform from minus 1/2 to 1/2. So therefore, if we had a column of n of these numbers, our error is going to compound, and our error is going to be the error of the first term plus the error of the second term plus the error of the third term, etc. Can we assume that the errors on each one of the rounding terms is independent from the others? Probably, right? Not always, but I think that's a very, very safe assumption. So therefore, the total amount, if X is a rounding error, we add n of them, then we are looking at the error, the total error is equal to the sum of all of the individual errors of those pennies that we rounded. So that's what the sum is equal to. What is the expected value? Well, the expected value of X is equal to 0, right, of an individual rounding term. And the variance is equal to 1/12 of a dollar squared. Square dollar. That's interesting. Square dollar. Because a uniform random variable has a variance equal to 1/12 of its range. And the range in this case is equal to 1. So the variance of X is equal to 1/12 of a dollar. In accordance to the central limit theorem, then, the variance of S is equal to n times this variance. And the variance of the sum is equal to n times 0. So the actual sum by the central limit theorem is a Gaussian probability density function with a 0 mean and a standard deviation equal to root n over 12. And this will be a pretty good approximation for n greater than 4 or 5. Be an excellent approximation. However, there's some sacrifices we need to make with the central limit theorem. For example, let's suppose that we added 3 terms. If we added 3 terms, we would get a piecewise quadratic sort of function corresponding to a uniform being convolved with itself 2 times. So there's three terms altogether convolved. So this would be the density function. And what we're doing with the central limit theorem is we're approximating this by a Gaussian curve, which I'm not sure exactly how it would go, but it would probably go something like this. And we're saying that those are pretty well near each other. However, you notice that this exact term doesn't go over $1.50. If you have three different terms in your addition, there's no way that you can make a mistake exceeding $1.50 either way, right? Yet your Gaussian allows you to have errors of $3 or $2. So the Gaussian says, yes, you know, the probability that you're going to have greater than $2 is going to be a finite number, whatever is equal to the area under here. That's what the Gaussian is going to give you as an approximation. And clearly that isn't true. The probability that it's greater than $2 is equal to 0. However, this number is going to be so teeny-weeny that it's going to be so close to 0 that the results are still going to be meaningful. So it's not a reason to throw away the central limit theorem. It's something that works very, very nicely. But with this, we can do things. For n is equal to 10, what is the probability the total error is over $10? 0, right? What do you think the central limit theorem would give you? 10 to the minus 37 or something? Yeah, it would be very, very small. Okay? So we can ask these things, but always do the sanity checks. De Moivre. This is a special theorem which is many times introduced in courses which are prerequisite to this one. I have heard it referred to as the Laplace-De Moivre theorem. It is the theorem which says the binomial distribution can be, for certain values of n and p, replaced by a Gaussian approximation. And it's historically pinned to Laplace and De Moivre. And why is a binomial the central limit theorem? Because a binomial is what? A binomial is a repeated Bernoulli trial. And when you do a binomial random variable, you're counting up the number of successes, right? And for one success, if you have a binomial, if you have n is equal to 1, you have a probability, say a value of q here, and a value of p here, corresponding to 0 and 1. And these are the values that you can have for n is equal to 1. This is a Bernoulli trial. If we were to take this result and we were to do 2 Bernoulli trials, well, that becomes a binomial random variable, right, with the parameters n is equal to 2. And that is obtained by taking the simple 2 points and convolving them with themselves. And if we take these 2 points and we convolve them with themselves, we'll get something which looks like this. For n is equal to 2 points, 0, 1, and 2. In a similar fashion, if we go up to n is equal to 3, we will get something which looks like this. And that's equivalent to this convolved with the auto-convolution of this 3 times. Or equivalently, this convolved with this. Okay? Now, this is what the binomial does, but you'll notice the binomial is an addition of IID random variables, the IID random variable being the outcome of the Bernoulli trial. And indeed, if we go to n is equal to 500, and we have reasonable values of p's and q's, this, if we were to look at the envelope, of this, we would obtain something that was very nearly Gaussian. Okay? This then is the Laplace-De Moivre theorem, which says that the binomial for very, very large values looks a lot like a Gaussian probability density function. Now, if we go up to n, what's the expected value of the number of successes? It's equal to n times p, if you remember, for a binomial. And what's the variance? It's equal to npq. where Q is equal to 1 minus P. Remember that? That's all we need to know. Because we said that if K and N are big enough, that this is a Gaussian random variable. So it's a Gaussian random variable with a mean of NP and a standard deviation of NPQ. This result is from the central limit theorem. Indeed, the Laplace-de Moivre theorem was something which was proven prior historically to the central limit theorem, but it turns out to be a special case of the central limit theorem, because it is a repeated summation of all of these values. So let's look at the math of this. If we could go to the slide. The sum of n IID Bernoulli random variables with success probability p is a binomial random variable. As n goes to infinity, the central limit theorem says this sum approaches Gaussian with a mean of np and a variance of npq. This is the de Moivre-Laplace theorem, which says that the binomial coefficient here, this is the binomial coefficient which appears in the binomial random variable, can be approximated by this Gaussian hump. And it's a specific manifestation of the central limit theorem. You remember we said all of these different animals, these different probability density functions maintain themselves. If you added two independent gamma random variables, you got a gamma random variable. If you added two Poisson random variables, you got a Poisson. If you added two binomial, you got a binomial. If you had two Gaussian, you got a Gaussian. Remember that? But notice something else. If you add a Poisson to a Poisson to a Poisson to a Poisson to a Poisson, you get a Poisson. But if they're IID, you also get a Gaussian, don't you? So that Poisson eventually will become a Gaussian. Similarly, if you add a gamma to a gamma to a gamma to a gamma to a gamma, yes, you do get a gamma random variable, but the central limit theorem says that that gamma random variable, which is expressed as the summation of all these other gamma random variables, is pretty close to a Gaussian. Okay? So all of this list that we gave before, and I have it duplicated here, if S is a Gaussian, then as n goes to infinity, it's a Gaussian, of course. But this is true if it's binomial. We just showed this for the de Moivre-Laplace theorem. It's a binomial. As n goes to infinity, it's a Gaussian. Poisson, if n goes to infinity, it's a Gaussian. Gamma, if we sum up a bunch of them, we do get a gamma, but as n goes to infinity, it becomes a Gaussian. Same thing for the negative binomial. And if S is Cauchy, if the S sub k's are Cauchy, as n goes to infinity, it's still Cauchy. So again, we always put in the Cauchy as the spoiler for the group to illustrate that this is not always true. By the way, what requires, well, we'll actually talk about sufficient conditions for application of the central limit theorem in a minute. So this is something else interesting. We have the Laplace-de Moivre theorem for the binomial, but there's also kind of a Laplace-de Moivre theorem for the Poisson, the gamma, the negative binomial also.
So
Yeah.
Does that mean that you should be able to tweak the parameters on the Gaussian to make it any of these others, binomial or Poisson?
No, it doesn't mean that. You will notice that in all of these cases, if we have a Poisson, for example, with a parameter of alpha, and we add it to a Poisson with a parameter of beta, then we obtain a Poisson with a parameter of alpha plus beta. Okay? Central limit theorem says is that if we add up a whole bunch of Poissons, we get a Poisson with a parameter equal to the summation of all of these, and that this Poisson will eventually become a Gaussian. But notice, it's only true if there's a lot of these terms. So it's only true if the summation of each one of the alpha n's is a big number. So a Poisson is not always a Gaussian. It isn't for small parameters. But in this summation, as the parameters changes, it becomes Gaussian eventually. And yes, if the parameter for the Gaussian is sufficiently big, then you can call it, if the parameter for the Poisson is big enough, then you can call it a Gaussian. Does that answer your question?
Is there an expression for how quickly you approach a Gaussian?
Very good question. Is there an expression for how quickly you approach the Gaussian. It's very dependent upon the underlying density that you have. So the answer is no. There is some actually work using something called Hermite polynomials, which attempts to address this question, but I'm not prepared to give you the results of those. Okay. So the convergence is not given here. Okay, in order to derive the central limit theorem, we have to address a fundamental lemma, which says that the limit as n goes to infinity of this parameter is equal to e to the minus beta, which is an interesting result. Anybody have a calculator with them? Do you have a calculator? One that takes e to the x's.
I do.
Oh, okay, good. This is what this says. So let's take epsilon equal to 10 to the minus fourth. Could you compute this? Let's see. Epsilon 10 to the minus fourth. Oh, and this should be a 1 over n, shouldn't it? Something should. No, that's fine. And let n be equal to 10 to the fourth, and then raise it to 10 to the fourth. See what you get? Now, let epsilon equal to 1. That's ridiculous. Okay, let epsilon equal to 1. Ah, see, 2.718. And what's e to the 1? It's about that, right? So indeed it does work. Right, yeah, it's kind of cool. Could you prove this? If I ask you to? Not the way we just proved it with the calculator, but prove it. How would you prove that? Huh? This is one of these 1 to the infinity problems, right? How do you do 1 to the infinity problems? Yeah, take the log. Let's take this out and just say that approaches 1 to infinity. Okay, and here we have a if we let n go to infinity, we have a what? We have a 0 over 0 situation, right? Which you can use L'Hopital for. Okay, so you'd use L'Hopital, and you would show that this is equal to, what do you think it's equal to? I think it's 1. In the limit. And then, so the log of x approaches 1, so that means x approaches e. Oh, yeah, epsilon, you're right. Oh, I put the epsilon here. Yeah, it approaches epsilon, so it's e to the epsilon, yeah. So anyway, this is an outline for how to show that. If you'd like me to go through more detail, I'd be happy to, but I think that should be enough. So that's a lemma, and that's a lemma that we will use. Another way to think about this, too, is that here's kind of the, you want to see the engineer's proof? E to the epsilon is equal to e to the epsilon over n raised to the nth power. Right? Right? And for small, I'm sorry, e to the minus epsilon. For small arguments, e to the, if we just take the first two terms of the Taylor series, which is valid for the exponent being a very small number, which is true for n being very big, it's equal to 1 plus epsilon over n to the nth power. Okay, for epsilon small. So that's another way to look at it, if you want to look at it that way. I like the L'Hopital a little bit better. Okay, so we have this lemma. And this is a lemma that we are going to use in the derivation of the central limit theorem. Okay, here's the preliminary results. Gosh, can we do this in 5 minutes? I will not rush. S is equal to the sum. Here's the z value. We know that the z value has a mean of 0 and a variance equal to 1, right? And now we will show the following. We will show that z, this value of z, has a characteristic function which, as n goes to infinity, the number of samples goes to infinity, always goes to an e to the minus omega squared over 2. This is the characteristic function for a Gaussian random variable. So what we will do is we will show that z has a characteristic function, asymptotically, that approaches that of a Gaussian random variable's characteristic function. Okay, here's a little bit of math. Here's the expression for e to the j omega z. Z is a function of n. If we just take the value of z and we substitute it in, we get this expression. This is just the s minus nx bar, etc. What is s? S is the sum, right? And this, in turn, can be expressed in this fashion. Now, notice what I've done is I've taken the s here, and I've written the s as the summation of the x sub k's. So I'm going back in the evolution of the derivation. So I've taken the sum and written it as the summation over the individual values, and then subtracted out the mean. So if this is this is the case, if the individual random variables are IID random variables, then this summation can be factored outside as a product. Do you agree with that? No, that's always true, I guess, right? This summation can be factored outside as a product. So we have the product of the individual values. So now we're going to take the expected value of this product. That's the expected value of this of the expression that we had on the last screen. Now, here's where they're IID. If they're IID, then the expectation value of the product is the product of the expectations. It's something that we've shown before, because they're separable. And the characteristic function for z is given by factoring this product outside. And then we have the product of a number of terms, all of which are identical. Each one of these terms is identical because they're IID. They're identically distributed. So that's the same thing as taking one of these products and raising it to the nth power, correct? So that's what we'll do, is we will take this expected value and we will raise it to the nth power, because each one of these terms is the same. Now, we will take this e to the j omega and we will expand it in a Taylor series, leaving this n outside but expanding this in a Taylor series. We expand this in a Taylor series and we get, if we keep the first two terms in the Taylor series expansion, we get this plus this, and here's to our nth power. Now, here's something which is interesting. If we take the expected value of 1, well, that's 1. But you'll notice if we take xk minus x bar, this term is equal to 0, since xk has a mean of x bar, doesn't it? So if we perform the expectation here, we obtain 0. So only the squared moment comes through unscathed. The first moment goes to 0. So we're left with this expression raised to the nth power, and that turns out by employing our lemma. Well, let's see. We get this expression, but what is this expression? What is x minus x bar squared? Isn't that the same as the variance if we take the expected value of this? Yeah, it's the variance. So instead of the expectation, we place in the variance. Here's the squared for it. Everything else stays exactly the same. Then we impose our lemma that for n very, very small, this is about equal to e to the minus whatever this is. And if n gets very big, then this term gets very small, and we are left with this expression here for the characteristic function. Now, we went through a lot of steps, but actually, if you look back at the individual steps, they're relatively straightforward. Each one is kind of a little baby step, and then, boom, we end back here at the central limit theorem by applying the lemma about this being a truncated Taylor series. Any questions at all? Okay, I invite you to look over this derivation, see if you have any questions about it. This derivation, again, is somewhat limited. It assumes that the individual random variables that we're adding up are IID random variables. I would remind you that the central limit theorem is applicable to cases where the random variables are not IID. Indeed, they need neither be identically distributed, nor need they be independent of each other. Okay, if there's no questions, then you're dismissed. Thank you.